So let's first introduce ourselves before going into some more complicated business. Yeah. So
Sure.
so if you just say something about what you regarding your academics, so that I can understood from where I should start.
Sure. So I'm Satish Tope. Excuse me, sorry. So I completed my Bachelor's of Engineering in Electronics and Communication. It was a while back, back in 1997. And I've been working in the industry on various domains. Actually, I started as a researcher in silicon technology development at Texas Instruments, and I've been working on the process node development, like C45, C25, 25 nanometer. Started from 180 nanometer down to like 20, 45, 28 nanometer, and then I left that industry, and then I went to architecture. So if you used any OMAP, if you used any Nokia phones in the past, you are definitely used to one of my architecture. This is basically the OMAP 3, OMAP 4 processors. So after exiting the chip design industry, so I went to product development. So I worked at Amazon. So if I use Kindle e-readers and Kindle tablets, then those are like I was the chief architect for those devices. So it's a system architecture front. So I was working on that for nearly like 5 years in Amazon. And then the last 12 years, I've been focusing on AI research. And right now I'm at Google doing AI research. And my research in AI, it's on foundational research. So like every couple of years, I change my domain of research. So initially, I was working on affective computing, which is dealing with the emotions, how to detect emotions, how to teach the devices to detect human emotions and sentiment, and then move to audio, where to teach the device how to recognize the speakers, how to recognize the different intonation, and so on. And then quite recently, I've been focusing on symbolic regression. So using Gemini, so I was part of the Gemini team. So I was part of the video enhancement on Gemini team. But one of the thought that I had in my mind is basically like these language models, the large language models, are perfect for communicating between like a complex data with the humans, the natural language of the humans. So that was the motivation behind me in going towards symbolic regression, because the data can be best understood if we can organize them, if we can get some insights with that. But this is one track. So in parallel, right from college days, like I've been focusing on physics. I want to do my career in physics, but somehow things changed, and then I set my career in engineering. So still, even nevertheless, have been doing self study on classical mechanics and quantum mechanics. So I've been like doing that for quite a while. I've got a chance to use those in my research, like in my industry domain, especially when you are dealing with like 28 nanometer gate oxide thickness. So you might want to do dopant fluctuation, so on. But it's like a very few use of what I learned over there. But so far, I've been doing mainly physical study of physics as like a kind of an hobby, kind of like my kind of my interest, my own interest. I didn't get a chance to use those knowledge in my industry domain. But recently, with the AI, I'm seeing there is an opportunity that can be found, especially in particle physics. Hence, now I'm taking it more seriously to see like how can I incorporate particle physics and quantum mechanics on day-to-day life. I mean, in my current research at Google. So that is the reason and motivation for me to get into this domain.
Okay. Yeah, that's really looks like and sounds very interesting. So yeah. So about me, so I right now working as a assistant professor. I think in here they call this as a you can consider postdoc fellow. So I did my PhD on experimental high energy physics. So my main domain of work was quantum chromodynamics, which is basically the today we'll talk about so bit. So where we basically talk about the interaction of quarks and gluons. So my main topics of research was basically search for the critical point. It's also one of the very fundamental concept in any physics, the critical point. Like if you consider water has like a critical point. Similar to that in QCT, also there is a concept of critical point. So that was part of my PhD. So which is basically the focus of heavy ion physics, because heavy ion is one of to also when you go further about different experimental artifact where we use a different instrumentation where the heavy ion is one of the very important tools. So we'll talk in details later. So I did my PhD on heavy ion physics, and then now I am trying to focus more into more in the larger context. So I'm now concentrated on neutron physics. So this is a different field of not related to my PhD what I did. So because I just wanted to learn more. So for me the neutrino was is one of the important stuff in, because I also interested in astroparticle physics apart from the heavy ion physics in quantum chromodynamics field. So I basically did my masters from University of Pune in Maharashtra. Then I did my PhD. My main station of work was in one of the experiments at CERN in Geneva. It's known as Na61 sign experiment, where it's basically dedicated for the heavy ion collision. And now I am an assistant professor in University of Warsaw, as you know. So here I am now mostly focusing on the neutrino physics. Also, apart from that, time to time I do some teaching.
Okay.
So that is a
quite impressive. Thank you, Dr.
because I always like to learn something new. So that's why whenever I get chance to learn, and also I believe that if I learn something, if I able to share my knowledge with someone, so at the same time I can learn more.
Yes, I agree with that philosophy.
Just doing something for myself and sharing my knowledge with someone, that's a different story. Yeah, so this is a kind of bit of introduction about me. And now related to course, what we are planning to do. So before going into so you can see the whiteboard, right?
Yeah, I can see the whiteboard. Yes. Yeah, I can see it very clearly.
Okay. So we can use this whiteboard whenever we need it.
Perfect.
So as I defined the course is basically introduction to particle and nuclear physics. So, but basically when we studied, it was we going in the other way around. So first we start with nuclear physics, then we go to particle physics. But I am thinking to make the course in a different way. So we want to decouple the two physics part, because neutrino. Sorry, not Newton. I'm still in zone of Newton. So we'll come it later. So in nuclear physics, it's a different part, and particle is a different part. But we'll try to make a connection between them. So my idea is we will start from some basic, and then we step by step first we try to understand some concept of particle physics, parallel nuclear physics, and at the end we try to merge them so that we can get a clear picture exactly.
Okay.
If we start from the classical physics, this is our real world, and then when we go to quantum physics, so we need to change the thinking of energy scale. That is very fundamental concept in any physics. Whenever you want to change from one domain to another domain, so we need to think about different energy scale, or in terms of physics, different length scale.
Gotcha.
So my main idea is to make the course is like more interactive one.
Okay.
So I hope you will not mind when we're going to discuss. I will try to ask some question. It is not to charge you, but I will be really happy if you also join in the interaction, so that it will not boring too much. If I supposed to talk and you listen to the homework, it will become boring at some point. So I will try to make the course in such a way that at the same time when I'm teaching or I'm giving some concept, some knowledge, try to transfer to you. So I will hope you also join with me so that
Definitely.
we can make it profit both of us. I mean, I can also learn from you. This is one thing. The second thing about homework. So like I already give you the GitHub
Yeah, I
page,
saw that.
and so in
Yeah.
the GitHub page, I'll upload the note at least one day before the class, and at the same time also some kind of homework, not really homework, some problem to solve, because in physics one of the most important thing is solving problem. Until
Yes.
you solve problem, I mean conceptually you can get some idea, but that idea could be more realistic when you try to solve some problem. So yeah,
Agreed.
and as you told, you are an expert on programming. So you can solve the problem on pen and paper, or if you want, you can solve the problem using Python or C++, whatever you want. So mostly the problems will be numerical one,
Mhm.
so that you can get some hand-on experience. Whatever you think we discuss in the class, so you can solve something. Yeah. So and the course will be, as you said, I'll try to focus or try to follow the Griffith particle physics or elementary particle physics book, which is I think one of the best book ever written.
Yeah.
I think like when we was like bachelor student, I think quantum physics, when we start to run quantum physics, Griffith was the only option for us. Not only option, it was one of the best option for us because it's easy to understand. There are
Yeah.
a lot
Yeah.
of problems, so we can solve and we can learn from it.
So which book you mentioned about quantum physics? Sorry, just
It start from Griffith, and then also we read quite few number of books. One of them was by Martini. I can
Martin.
I can give you the link of all these books. Which and there are also uh, there is, if you want to learn more in advanced in quantum physics, which is quantum field theory. There is a very famous book called by Peskin, one of the
Mhm.
guy from Oxford or Cambridge, I guess. Yeah,
Got
course I'll mostly focusing on Griffith, and also the course structure, as you mentioned, the lecture series from MIT.
Mhm.
But today's class I try to not try to make it more general.
Mhm.
So already, if you see the notes, which is handwritten,
Yes.
so it is readable or not, because I was just make try to make some sketch what I want to discuss in the class. And this is one thing. And the last thing, whenever you feel that I'm going too fast, because I had that bad habit
Mhm.
very fast. So if you feel that you miss something or you're not able to catch up something, then feel free to stop me, because
Sure.
it's not that only I should talk. I mean, it is you should understand whatever I am talking. So related to this or logistics, if you have any problem at any point, you can just stop me, ask the questions. It could happen that instantly I cannot give the answer. That's because the field is so vast; it's not possible to answer all this instantly. But definitely, we can think together. We can try
Mhm.
to find a solution together. And when I am teaching something, obviously I prepare some notes. So if something on that question, particularly on that, definitely I should have answered to that. But apart from that, if you want to uh, discuss anything related to physics. So as I mentioned, this voice application, which I think it's a really good application because it's a very nice interface. So there is one place where you can also ask some question and we can have a discussion there.
Got you. Got you. I have Dr. Hardhan. I have one question
Ah,
actually. Like,
you can just call
just
me by name, or
no,
it's
no, no.
I
That
don't really like it. Yeah.
no, the Indian tradition. I want to follow Indian
No,
tradition.
I don't. You can just call me by name. It will be enough.
Okay, 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 Hardhan. So, I actually like the critical question I have is like in if you take quantum mechanics, it's mostly about like solving problems. It's like you have to. It's my understanding. Please correct me if I right or wrong. The way I understood about particle physics is like so far what I've read, people have discovered something. the goal is basically to learn what they have discovered. Like for example, if it is a standard model, okay, what are the different laws of conservation of energy? What are the different fields, and how we think about quantum field theory, how we think about quantum chromodynamics. But there is nothing to, I mean, of course, everything has problem-solving things. But when you compare with quantum mechanics and particle physics, is more about knowing stuff rather than solving stuff. In quantum mechanics, is more about solving stuff, because whatever we know, I mean, like whatever we want to learn, it can be learned within like 1 or 2 chapters. But rest all is about like, okay, solving a wave equation in a boundary with a particular boundary value condition, solving a wave equation in this particular scenario. What happens in that scenario? How to solve a wave equations? Like you need more and more calculus over there. But here in particle physics, it's more about knowing knowing a lot of different things, like what are the different quarks and so on. Is my understanding correct, or what do you think?
I can say that it's 90% correct. I mean, in particular physics, or like, okay, if I say in a naive way that the concept of particle physics or in any kind of high energy physics, you need some basic fundamental knowledge first of all,
Yeah.
and that fundamental knowledge is like quantum mechanics, relativistic kinematics, which is I think one of the biggest tool. Then quantum field theory, which is the advanced one, but and then quantum chromodynamics, and so on and so forth. So now, so the basic problem what you can solve, it is part of this prerequisite, like in quantum mechanics, uh, quantum field theory, and some of these things. Now, when you reach to the field of particle physics, it is more into experimental.
Yeah.
This is one thing. The second thing is like in concept of particle physics, still now, I mean, it is still developing subject.
Yes.
Like quantum mechanics, you can say at certain point it's reach up to some limit where one can say that okay, I know bit of quantum mechanics, or still quantum field theory. One can claim that okay, I know bit of quantum field theory. But in case of particle physics, still now only a minor part of particle physics, the whole domain was discovered, understood. There are many things which is still not discovered. So
Okay.
so now when you are talking about the solving problems, so particle physics is not something really like realistic problem. I mean, it's not like if you not solve some problem, you cannot get some food. It's not like that realistic, not like classical one, right? So in
Yeah.
classical physics, we can easily make some problem. We can try to solve some problem based of our classical intuition. But or even in statistical physics, because that is a like domain where we can imagine easily, or when we can
Hmm.
think about it. Uh,
Correct.
in particle physics, one need to know first of the basic things which one can by imagination one can learn. But when we reach to the field of particle physics or nuclear physics, it is not in our scale. It is, I mean, at the beginning I said length scale. It is not in our
Yeah.
length. It is the length scale is very small, like of the order of 10 to the power minus 50 femtometer, or
Mm.
10 to the minus 15 meters. So it's like 1 femtometer scale, or even lower. So the only thing, if we try to learn more about the structure of like fundamental particles, then it is beyond our imagination. So we need the detector, and that detector will help you to understand the fundamental constituent like quarks and gluons. That is now till now it is a fundamental one. Then there our imagination would not work. So we need
Mm.
to on the nature. What nature will give us, we have to take that output as the fundamental one. So that's
Gotcha.
one of the probably reason that in particle physics or nuclear physics, or even in nuclear physics, still there are a lot many problems. One can do take a pen and paper, do the calculations, and but in particle physics, so there are theorists who do a lot of calculation, because any experiment that is based on some theory, or in
Mm.
other around, there are some experiment which leads to the theorist. So that's why in particle physics or nuclear physics, if we want to really understand, to get some input from it, some take-home message, we really need to first know some of the basic. When the
Mhm.
basic will be clear, then we can go more deeper into particle physics.
Gotcha.
So
Gotcha.
that could be the one of the reason why it's difficult to find some problem easily to solve, because these problems could be come out of someone mind, because there may be
Mhm.
more deep, and that problem could be solved. And
Gotcha.
so
Gotcha.
but that problem may or may not be very realistic, and that scenario will be experimentally verified by some experiment with a giant detector, like in Geneva and they had a giant
Yes.
detector, and they had a very high energy, now up to TeV energy scale. So
Okay. Okay. Super.
so now now I think 2027 there will be a shutdown, and so they try to upgrade it more. So
Okay. Okay.
we want, suppose, like when we discuss later. So we try to understand when we can change what is the length scale, when we can move from the classical field, I mean our energy scale, to quantum, then from quantum to more into nuclear. So you can understand that, like when you go to move to atomic physics, so
Yeah. Yeah.
the length will be of the order of atomic nuclei.
Yeah. Yeah. Yeah.
So now, if you go into more into deep, like if you go into the proton and you want to see how the protons are made with quarks,
Yeah. Quarks. Yeah.
we need that energy scale.
Yes.
So
Yeah.
there
For that,
are,
we need to go in the
there are,
10 electron volt or like even more electron volt.
yeah, I think it's up to G, at least. I think proton mass is few hundred MeV. So if you want to go inside to see the structure of quarks and gluons, you have to go up to the GeV's energy scale. So it's not that there is no problem. Obviously, there is problem. That's why field is still growing. If there is no problem, probably physics would stop at some point. But there are problem. But that problem is not something like classical problem.
Yeah. Yeah. Something that we cannot imagine or visualize. We cannot think about. We don't see in the real life. And
We
sometimes
can
we cannot
think.
even
Yes, we can
comprehend.
think. One can think. I mean, it's depend. I mean, physics is start from imagination, right? I mean, even the science is
No,
like.
what I'm saying is like I can imagine a classical problem of like throwing a ball with air resistance and so on, and then I can see the projectile. All those things I can like visually I can visualize. I can see it. But when someone tells me like the mass at that time, the decay time of a subatomic particle is going to change based on the velocity, we cannot comprehend. Like yeah, we cannot. Yeah, we requires a lot more imagination to think about and
Yeah,
visualize it.
like today when we discuss about this relativistic kinematics, as I mentioned. So the one thing, there is many kind of frame of reference we need to think. One is the rest frame of reference, or we can think about the moving frame of reference, or we can think about the frame is called center of mass frame.
Central mass wave.
Yeah, so that's something imagination, right? Center of mass frame is really doesn't exist in a physical way, but we can think there is one particle, there is another particle. So they are moving each other, they collide, they produce some particle. So we can think in that way that okay, this is at rest, and there is one particle is moving.
Uh-huh.
So now you can imagine the situation. Okay, you can imagine a frame of reference or your lab. Suppose this is your experimental lab. So you're sitting in the experimental laboratory where this particle, which is at rest. So you can think,
Mhm.
okay, it's my own frame of reference.
Mhm.
With respect to this one, this object is moving in this direction. So this object is coming and then hit upon this object. So now when you are sitting on the experimental laboratory, this is a particle which is at rest, and this is a particle which is coming and collide. So with respect to this one, this is a moving one, right?
Yes.
Now you can
Yes.
imagine, okay, I can change my frame of reference. Instead of taking this is my frame, I can go into that particle. I can sit on the particle. So when I sit on the particle, this object will be at rest
Rest.
with respect to that particular frame of reference. But
Correct.
but this one is now moving in the opposite direction.
Yes. 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 Yes.
The concept
Yes.
of relativity is same like you are sitting on the train. So
Pain. Yeah.
the train, your object outside is moving in the backward, which
Yes. Yes. Exactly.
and then you can think in that okay, instead of considering this is my frame, but this is my frame, I can think some imaginary frame somewhere in between them in such a way that I can think this was initially at rest, but I can think an imaginary frame with respect to that imaginary frame. I call it center of mass frame.
Center of mass frame.
Both of them are moving, but they're moving in such a way that
In
the
opposite direction.
momentum will be zero. So that is a kind of concept of called center of mass. So we'll talk in details there. So this is kind of imagination there. It is still you can think in terms of your classical intuition. Okay, I can imagine there is a frame with respect to that frame. This object is moving. This object is moving. But that is still classical. But when you go to the field of quantum mechanics, like there's one particle pion that decay into two, or some decay reference frame, then you can think, okay, I can sitting on the pion, but that's not really happen. You cannot sit on the pion really. But you can imagine, right? So imagination is always there to solve some problem, but that problem should be realistic. But in case of classical, statistical, quantum mechanics, I'm still in quantum mechanics. You can still imagine like a particle in a box. You can just imagine a particle, but that is not really the case. Particle is not really in the box. Yeah, so that is a kind of situation in case of particle physics. That, but there are many problems. We will try to when you go step by step. There are many problems. Like if you consider Feynman diagram, which is one of the very uh, beautiful and very nice theory given by Lord Feynman. And so when you think on that, there are many problems one can solve. Till now, there's many unsolved problems what one can imagine in terms of Feynman diagrams. So we have a scope to solve problems, and we'll try to develop our intuition step by step in such a way that we will able to solve some problem. Okay. So in today's class, the first thing I will start with some fundamental concept. It is very important. We use this concept several times throughout our discussions. So few of the concept we used. One is called units in high energy physics. So this AC stand for high energy physics. So in high energy physics, whenever because when you try to solve some problem, there are many times like, okay, let me tell you what I mean by this unit, like c, speed of light. This is one of the very fundamental quantity, and it remain invariant in all frame of reference.
Correct.
Whenever we define something called some fundamental units, that means this quantity will remain invariant. Suppose one photon is moving in one frame, in your frame or in my frame. The speed of light or photon, speed of photon, it will be always of the order of 3 times 10 to the power 8 meter per second. So this is the fundamental one. It does not depend on the frame of reference you are considering. And in high energy physics, usually we consider this C as 1. So we call this a natural unit. So physicists are lazy and they don't really like long derivation with like if you try to make a calculation of 100 pages and in every line there is C. So they're like, okay, let's consider C equal to 1. So we use this notation throughout our discussion later or today. So this is one thing. Can you guess any other fundamental quantity?
Planck's constant.
Exactly, Planck constant. So again, there are two kind of Planck constant. One is this H, which is of the order of 10 to the power minus 34. Can you guess what unit it could be?
Unit E is equal to H nu, so the joules per joules meter.
Meter, is it in terms
yeah, E is equal to H nu, so E is joules and then
right?
Frequency hertz.
So it will be second, not meter, because
second.
So
sorry, it will be second, joules per second.
So, but we don't really care about it. Like again, physicists are lazy, so they just consider these or h bar, which is a reduced equal to pi, reduced Planck constant, which is also of the order of 20 to the 34, and they consider this is equals to 1. So this is two fundamental things. At least for today's class, we we always consider this is one. So we don't want to make our life more more complicated, because already life is complicated. So this is one thing I wanted to discuss. And can you guess any other quantity which one can make it considered a one?
With respect to quantum physics or with respect to classical?
Yeah, with respect, let's consider quantum mechanics, quantum physics.
Okay. I mean, I would say like I'm thinking of like Coulomb's law, where we get the epsilon, so we can think that as a one.
But you need to think something which will be like general, like we consider Coulomb laws. So okay, before going back there, so this is what you just, I think few minutes ago when we were just chatting with each other, you are mentioning the standard model. So our main, when the last class will reach, our main goal will be understand the standard model of particle physics. Why it is called standard model of particle physics? Because this is whatever you can think in terms of physics or in terms of particle physics, the fundamental thing, everything we can get from this small and very beautiful diagram. So here, let me define. So as you know, okay, let me ask the question. So how you define something is fundamental?
Uh,
So this is the word I will use.
so everything is built from that.
Sorry.
Yeah, like a thing is. I mean, a thing. A thing is like that could be like a particle, that could be a unit, that could be whatever. If that is the basic unit is indivisible, we cannot divide beyond that. Then we can call that as fundamental.
Yeah, exactly. So also in the same way, when you define this something fundamental units, so the same concept we will also use here when you call fundamental. So it will be like true for everything. Like I mean, like when you go to the force in nature, as you know, we have four fundamental forces in nature. If we start with gravitational force, which is we all know belong to the classical field. Then we can go to electromagnetic field. So here I use a term field. So this is I will explain what is the field mean. And if you know, you can tell me what is a field. But
No, that's the most confusing concept for me, between field and force and particle and yeah.
The final take a message from today's class. When I'll conclude the class, at least we will able to understand what is field and what is particle. Okay. So for now, we consider there is a four fundamental force. One is the gravitational force. One is the electromagnetic force. So electromagnetic force basically, if I say in a naive way, that it is constructed by electric and magnetic field. So basically, field is a classical, not classical. I mean, it's a semi-classical or quantum mechanical. I mean, even you can think in classical way also. Like something is extended throughout the whole space up to infinite, which is extended up to some like up to infinity, to minus infinity plus infinity. So let me also tell you one more thing. In whenever you think in terms of quantum mechanics, quantum field theory, or particle physics, how our understanding is basically developed. So whenever we construct any physics, so first we try to develop the physics in terms of finite system, and then later we define or extend our space, or like in classical mechanics. Okay, if I try to define what is momentum, I'll come back. I will come back all the questions I already reached, but because I just wanted to have this thing on my board. So suppose I want to define momentum, classical system. There is no quantum mechanics. Forget a minute. So I want to define momentum. So how we can define momentum?
Mass time velocity.
So
That's a formula. Yeah, moment.
it is a general word, mass time velocity. But we can think in, let's consider one part. Let's first draw me a frame of reference, x and y.
Mhm.
Now, one particle, let's consider there is a particle at this point. And then I can define a vector here. Let's define as an R1 vector.
Mhm.
And this particle is moving and is reached up to this point.
Mhm.
Let's take this as R vector. Then we can calculate what is the distance traveled. Let's define delta R. And this is the time taken to travel from here to here, from this point to this point. Let's define is a delta t.
Mhm.
So now if I want to define momentum, so what will be my formula here? So the particle is moving at delta r
Yeah,
distance.
so delta R divided by delta T, that's the velocity.
This is delta r of delta t. So this is the basic concept of momentum, right? But now there's something like delta t, and it is not very general.
Yeah.
I want to generalize it. Obviously, there will be mass term for scale, otherwise it will not be momentum. So there's mass time velocity.
Yeah.
Now, so if I want to make it more general, so I need to take a limit. Let's consider the particle is moving from t is equals to 0 to up to infinite time. So if I take this limit tends to infinity, delta r over delta t with a mass term, that will give a more general definition of momentum.
Okay.
So when I define momentum here, this is a specific scenario that particle is moving from this point to this point. Now, question: what will happen? How to define momentum if the particle is moving from not here to here, but here to here, or here to here, here to here? So, to get a more general idea, we first define the concept in a finite system. I define a particle is moving from this point to this point. It's finite, right? It's finite. Now you can okay, I can generalize it. So I can take a limit up to infinity.
Okay. Yeah.
It's a very basic concept, not only in classical system, it's also true for quantum mechanics, true for particle physics, quantum field theory. In quantum mechanics or quantum field theory, whenever you try to solve any problem, the first, I mean, you can remember in quantum mechanics, as you already studied, we always consider boundary value problem.
Mm.
We consider particle in a box. So there's a boundary.
Yes.
So we want to define the system in a finite system. Finite. That's why the reason this boundary value problem or particle in a box problem is so famous, because it's a finite system. Now, if you want to think the system like infinite, so when you want to generalize it, then you later you take the infinity.
Mm.
So this is a very basic concept, a very fundamental concept. We use several
Okay.
when you go later, some calculation, abracadabra. Then this concept is always there. First, you start from finite,
Finite
then you go up to
and
infinite.
extend to like a more generalized one.
Exactly. Suppose you want to make an application or like
And even Einstein did the same thing, right? I mean, he started with special theory of relativity and then moved to general theory of relativity.
yeah, I mean, though it is supposed to go in other way around. So we first start with general theory of relativity, then come to special theory of relativity. But because of this one, as you said, we start from special theory of relativity. You see the special case, then you move to general case.
General case, yeah.
So when you know the special case, then okay, we can think more. So this is very fundamental but very important. Okay. Okay, I was talking about the field. So now, for a second, instead of considering an infinite space, I just instead of taking infinity, I take a finite space.
Yes.
I can later extend that. Now here, if suppose you want to measure something,
Mhm.
let you want to measure what is the moment, what is the electric field at this point.
Mhm.
Suppose there is a force, a charge Q is moving with velocity. What amount of electric force this particle can express, or this particle can experience? What amount of force it can experience? So we know also there is a magnetic field. And consider there is electric field and in terms of magnetic. So consider it's a vector quantity, so I can take that first. So if I consider that the charge here Q, it is now if I want the force, so the amount of force will be experienced by this charge particle if it is the same velocity throughout this region. It will experience the same amount of force here or here or here or here.
If the
So
velocity is the same, the force is experience the same.
uniform at any point. And so when something is uniform and extended up to certain point, so whatever any kind of physical quantity you are measuring at any point uniformly throughout the whole space, you should experience the same kind of physical phenomena.
Mm-hmm.
And that particular space or that particular concept, actually field is not some real space, it's a concept. Field is not something really field where kids are playing. The concept is coming on that way. So field is something extending up to infinity. If you play here or here or here, you should, if you're a good player, you should get the same result at every point.
Yes.
And this is about the field. And what is particle? Now suppose there is some excitation at some point. You drop it. Suppose this field is extended uniformly and there is one particle drop on it. So when it excited the state, earlier it was uniform in excited state. So whenever any excitation happen, then it's generated particle or antiparticle. So here I used to word something I did not say earlier. One is particle and antiparticle. So particle is basically mass, like when the universe was created. So there is a uniformity between matter and antimatter. Now I think this is one of the hot topic in many different experiments to study about matter and antimatter asymmetry. Asymmetry means in the beginning, matter and antimatter create the same amount, so there is a symmetry.
Yeah.
But when the system after the Big Bang system evolved with time, after that there's a cooling and then they further hadronization. Then when they measure the symmetry between matter and antimatter, there is a real. So there are many experiments going on nowadays to basically study this matter antimatter asymmetry, which come to a new picture of dark energy, dark matter, all these things. So when I'm talking about matter and antimatter, that's actually the corresponding of this particle and antiparticle. So in quantum mechanics or quantum field theory, probably you could remember the first time the concept of antiparticle came when Paul Dirac he tried to solve a very basic problem. Instead of using the Schrodinger equation, he tried to develop his own formalism, and then he found there is a negative energy.
Yes.
And the source of the negative energy, when he tried to explain, he was imagining that could be there is something which taking the energy, and how the antiparticle concept come up. The same thing also you can think in terms of when you try to solve this hydrogen atom problem or quantum mechanical Harmonic oscillator problem. So we can create we will discuss today about different operator like annihilating operator, creation operator. So this kind of concept are very fundamental, will come into the picture, but that everything is connected with the final concept particle physics.
Gotcha. I mean, I always had this question about this antimatter. Like, I understand that we are able to observe, like when electron and positron, when they annihilate, they give photons. So all those things we are observing, we are able to observe. But my question is always is like, I mean, the way that we do our calculations is like, okay, antimatter is something like even in Feynman diagram, it is something that arrow going backwards in time. So that is how we try to solve problems and so on. But why can't it be like a real particle? Why can't just like when I'm just drawing a parallel over here, just like we are saying that the charm particles and the strange particles in the in the fermions are not available after Big Bang theory. Now we are left only with quarks. Yeah, we're left only with like quarks.
Matter.
This charm and sorry.
Yeah, with
Yeah,
matter.
yeah, with matter. So Charman is not available. In the similar way, the antiparticle is not available because it's the same explanation that we can give for charm can be given for antimatter also. But we don't do that. I don't understand the reason why we don't do that. Like, yes, it may have a similar properties, exactly opposite charge of electron. But why can't we think in the same way as like what we think for charm particle? Why can't we think the same way as for the positron?
Okay, so one of the simple answer it could be because of the energy. So till now,
Uh-huh.
all the detector we have and the human-made detector, like even if you consider the sun the highest energy up to some TV, but still it is not well enough to really do this one-to-one in analogy because the energy scale is so high, the lens
Mhm.
is so small. Before to do this one-to-one analogy is because okay, you can do this thing on pen and paper, right? This is you have the full freedom to do it in pen and paper. But when you are experimentalist, you are doing the experiment at some kind of complicated detector system, and you are want to discover something. But one of the main constant will be the energy or the lens scale. So whenever you want, suppose you want to, if you are thinking like when the first time this concept of antimatter was discovered, uh, I think it's one of the in Brookhaven National Laboratory where they did this two proton. I think one proton was raised, one proton is coming, they collide. So the reaction was something like this. So this E stands for proton. So two
Proton, yeah.
was interact, then is moved. I think three proton and one antiproton. So
Okay.
that one, the energy range was few hundred MeV. And on the time when this was done in Brookhaven National Laboratory, that time to think about that energy scale was very difficult because the technique was not that well developed that one can generate that energy, one can collide two particles, or in that energy, it can produce a new state. Like you can see here, you have two particles which are basically collide. They are basically high energy particles. They collide, it produces four particles. So one thing is very very common. Maybe if you think in terms of classical one, it's not possible, right? You are colliding
Yes.
two particles, you get four particles. How that could possible? But thing is happening here. These two, right? It's create one proton and antiproton. So even
Antiproton.
imagine in this way that these two proton was given as it is. If you just it may be just exchange the energy between themselves, and that energy is converted into matter.
Uh-huh.
That matter actually created in proton and antiproton. So
Okay.
and that energy scale was so large at that time when this was discovered first time in Brookhaven National Laboratory in BNL. This was something is unimaginable, that energy scale. Now, if you want to go into charm particle, and if you see the mass of charm, and if you want to really go to the antiparticle of this one, I mean, go into this one to see how the dynamics work, your energy scale should be larger than the rest mass of this charge. Now, whenever we talk about now, at least in particle physics era or in this domain, whenever we say mass, it's supposed to be rest mass. Rest mass means the mass in that particular frame of reference.
Yeah.
So this is also one of the very fundamental. I think okay, that actually the one thing just remind me. I asked in the very beginning of what is
What is
an
the fundamental?
fundamental quantity you can think which could be one can take one. It could be race mass because it's something if you whatever the race mass in my frame of reference, and if someone is thinking on other frame of reference,
That is interesting.
then the rest mass, suppose the rest mass of this object should not change. It can change with respect to other frame. But suppose this is moving. This
Okay, okay. I see what you're saying. So basically, like, if the mass is moving, then definitely from my frame of reference, that mass is different. But from that frame of reference, the mass will be the same as what I see when I'm in my frame of reference.
That is not something really used, but I can imagine in that way. If I something I want to think more fundamental, that suppose my race mass in my frame of reference will be always same. Like
Gotcha.
I think it's one of the fundamental concept in relativity that that you can change the frame, you can change the environment, but the physics will remain invariant.
I think that that's always have one more problem for me. The time, with respect to time, the same concept with respect to time. Like the clocks run slower at the higher speed, for example. I mean, highest like so the thing that I mean, I understand like it has been observed in part. I know we are like we are going beyond what what the introduction class is,
No, it's,
but
you're full freedom to ask whatever you want. I
yeah.
will try to at this understand your question. Probably I could not answer instantly, but at least I can understand. Try to
Yeah.
understand.
So the question I had is I always think about like you said, like rest mass is the fundamental concept in water frame of reference. Like the frame of reference must be the same. Like you might be moving, but according to you, you are at rest. So the
Yeah.
particle that you would observe, the mass that you would observe is having some value. And in my frame of reference, the same particle or similar particle will have the same rest mass. I understand that. But then when it comes to time, right? When you are moving and you are thinking like you are saying that your time is shorter. So, yeah, time is shorter. According to me, yeah, according to me, your time is shorter. Like I mean, the clocks run slower for you.
Time
According
will
to
die.
me, the clock runs slower,
Yeah.
right? But for you, the clock should be normal.
Yep.
But it is not the case, right? I mean, like if it is normal, then your decay or like your clock should say 1 second. But if you're traveling close to the speed of light, your clock stops. Why should it stop? Then how can that be
So,
fundamental?
so actually, in relativity, is there is one quantity we always define. Instead of talking in terms of time, we define one quantity is called space-time interval.
Yeah.
So,
Okay.
we always, according to the basic definition of relativity or even the general concept, that probably your length can be contracted, your time can be dilated. So your clock could be may or may not be synchronized.
Oh, okay. I see what you're saying. So length is contracted, time is dilated. So
But
the product
the
is the same.
space-time interval, like if I define, uh, I will come back to this one later. So if I define one event, I call define as E1, and according to definition of four vector, I can define is like CT and let me consider R. And as I am lazy, I can just remove this C. As I mentioned, this
Mhm.
is like fundamental init. I don't use T here because anytime you can you come back and you can see okay, this is length, so this there should be C just to make it dimensionally correct.
Mm.
And you have like defined this one. You have another unit, another event, T2 and R2. So these two events could be different in different frame of reference, but whenever we try to calculate with something called space-time interval, which it will be like t square minus r1 dot, because this is a scalar quantity, so I can make that like not t square but t1 t2. Like say t1 t2. So I take t1 t2 and r1 dot r2. So this will be what will be my space-time interval. So your time may or may not synchronize. Your length can be contracted, time can be dilated, but this quantity, the space-time interval, it will be always remain invariant.
Yeah, yeah, okay.
So that's why whenever going to the concept of relativity, then we don't really talk in terms of the this quantity, because this quantity can change. So that's defined how the Lorentz contraction happen. So
I see, I see. I think I read in Griffith, like in related to kinematics, where there is invariant quantity and covariant quantity. So invariant quantity is this one, yeah. T
exactly.
square minus one minus R2 R2.
Something will be remain same in all frame of reference. So now when
Okay.
we talk about the in relativity, there is a two type of transformation we have. One is called Galilean transformation, and one is called Lorentz transformation.
Okay.
Lorentz
No,
transformation means that your speed of the object is very high, is of the order of speed of light. Not if it is very small, it will be classical. The Galilean transformation is a classical transformation. So if you move from one point to another point, you know how to calculate the distance between them, how to calculate time between them. It's a classical one. But when you are moving at a very high speed, not like a speed of bullet train, it's far better, far larger speed of light, of the speed of light. Then your system is no longer classical or no longer non-relativistic. It becomes relativistic.
relativistic. Yeah.
And your position and time they start to mix with each other.
Yes. I understand.
The same thing also happens for energy momentum also. So whenever we consider energy and momentum, we define an energy momentum tensor like 4-vector. And then if we put this 4-vector in Lorentz transformation, I mean speed is very high, it's moving with a very high speed, then the energy and momentum, so energy is like a geoth component, it is a scalar quantity, and momentum is your vector quantity. They start to mix up with each other. So this mixed up is not a classical one. It's actually some relativistic one, and then we don't talk about this one anymore. So if you understand the physics, we need to think here this interval.
Okay. Now I understand like why this invariant is used. Thank you.
Invariant general one is exactly the English word. Invariant is something which does not change. How to define change? Like when to define velocity, we define the position is changed with respect to time. Now today, when I do some mathematical calculation in terms of relativistic kinematics. Now, okay, suppose let me we'll come back to this later. So now suppose when you define momentum in the classical system, as I already discussed. So momentum is defined like take the limit, delta t tends to 0, delta r over delta t. So whenever you consider a classical system, this is the momentum. Obviously, your mass term. Now, when you go to the now, if my system is moving with a very high speed, a speed of light, then as I mentioned, this t, the time is not something which is invariant. It could be dilated, it could be contracted, it could be changed, like depending on the which form of reference you are. So now, if I want to define a quantity called momentum in the case of relativistic cases, so is that this delta t, can I take it that time there? Because so this thing which itself is changed. So now when we go to relativity, then we don't talk about this time. Instead of that, in mathematics, we define another concept. It's called tau.
Popular time.
Exactly. So we define something like delta t, which is contracted by d square over c square, and this quantity we define as a gamma, which basically is Lorentz contracted term. So we use this quantity instead of using t, because this quantity is not a fundamental one, because it can change with time. So we want to define, so whenever we define any kind of physical quantity, we always think about fundamental one. What's the fundamental one? Which is not change with time. Which is, I mean, it doesn't matter in which frame of reference you are. You can change your frame of reference. You can here, or you can in three-dimensional space in different orientation. So you can change your frame as you want, but what relativity tells you that it does not matter in which frame of reference you are, the physics will be remain invariant. If the object is moving here, you can see this is the physics. It will not happen. That frame of reference, this object is going up. The physics will be remaining. Maybe your way of interpretation will be different. You can, because you rotate your frame. So you have to think your rotation frame. I am just looking like this. Like for me, it's just object is moving. But who is rotating? For him, it could be like something else, but it should move down. So that's
got you. Understand.
Of not only relativity, but in any physics. Like your fundamental physics will be remain invariant. Like even when we will talk about classical system, quantum system, or microscopic or macroscopic state, in statistical mechanics we use one word. It's called microscopic and macroscopic state. So microscopic is like a time dynamic of, let's consider electron, proton, or in the microscopic scale. And macroscopic is a classical system. So if you want to understand your classical system, you need to think in terms of your what happened in the microscopic space. Because whatever thing is happening in this microscopic space, the ultimate result will be you can reflect in your macroscopic space.
Yeah. Okay.
So, but concept is whatever the physics is happening in your microscopic phase, the same physics should happen in your macroscopic space.
Got
If
you.
it doesn't happen, it's your problem. Your detector is wrong. Your experiment is wrong. Whatever you're thinking, your way of thinking is wrong. So you need to modify your thinking in such a way that it does not matter in which frame you are, but the physics should be remaining.
Got you. Okay.
So that's your answer of your question, that why we think in terms of, because time can change, time can dilate it, but we always think in terms of which is invariant.
Got you. Okay. Hardan, sorry to today I have a hard stop at in 25 minutes. I have another meeting.
Okay.
Just 25 minutes, not now. 25 after 25 minutes.
For 25 minutes, right? Okay.
Yeah.
Okay. So till now we are talking a lot of nonsense, but doing something which makes sense.
Okay.
So okay.
No, I mean just one thing. Like I studied I read the invariance. I understood the mathematics what they are saying, but I didn't know where to apply. And you explained where to apply, so it was useful.
Okay. So probably, as you said, you had 25 minutes or something like that. So let's try to do something which could be mathematically again interesting. So I can maybe move this part to.
Yeah, sorry about this. Like Saturday will be fine. Like we can take as much time as we can. But just today, like have a meeting at.
Yeah, understood. Because I changed the time because it's not your problem. Because yesterday I supposed to. It's usually I had a holiday on Tuesday and Friday, Saturday, but there was some guest in the faculty, so they asked, being a newcomer, so they want to introduce something. Okay, so let's continue with this one instead of going to more general one. Let's focus on this relativistic stuff, because this is very fun, very important one, because whenever to go further, kind of concept will be always like the invariant one. This is one of, like, there is one very popular theorem in quantum field is called Noether theorem. Noether is, I think, she is one of the lady. So it's that okay, if in your system, if there is a any kind of conservation, okay, when I say conservation, something come in my mind. So can you guess what kind of fundamental conservation one can think in particle physics?
In particle physics.
Or in high energy? Or in quantum?
Like a conservation of energy, I can immediately think of.
Okay. And
conservation of mass.
Conservation of mass, like let's just few minutes ago I wrote one equation. Photon goes up to.
Yeah, you know what? I mean, when you wrote this equation, I want to ask this question, but I thought, okay, when we're discussing on conservation, we can keep it for that moment, actually.
Okay.
Yeah, conservation of mass is something that, okay, in high energy physics.
So this is not high energy physics is true for any kind of non-relativistic, any kind of relativistic case.
Okay. So conservation of energy, conservation of
one thing also
momentum, conservation of momentum.
Yes, angular momentum is not very fundamental one, but momentum is very fundamental one.
Yeah, so conservation of momentum.
Energy and momentum, which is very fundamental one. Like when I as we already talk about this one, so like in this example, in high energy physics, in relativistic cases, you can see the mass is not conserved here anymore. But in classical system or in non-relativistic cases, usually mass is conserved. I mean, because otherwise mass can be, according to Einstein, the great boss, mass can be converted to energy. Actually, this is what happening here. Because the mass, these masses are because of the energy is converted. Because these two momentum, these two protons, which are colliding, they are very high energy. So when they collide with each other, they exchange their energy. So that energy is converted into mass. But here again, thanks to the boss, energy is not only mc square, but this is still non-relativistic.
And classical.
Here, when I'm talking about m, this m is a rest mass. Rest mass means this is a mass on the frame of the particle. So it will be always rest mass. So like if I think about photon is one of the very peculiar particle in the whole system of standard model, because this is one of the fundamental particles, because this is belongs to the standard model, and which basically interacting particle. Suppose there's two charge particle, they are interacting with each other. We will talk with later details. So these two particles which are interacting, they should be fermion, because they obey the Fermi statistics. So when the two fermion they interact with each other, there should be one particle which be exchange between them. So photon is one of these bosonic particle, and that particle should be bosonic because they should follow the Bose-Einstein statistics or Bose statistics. Thanks to India, we had our own genius Bose. So that particle should be for the Bose-Einstein statistics. So this photon is one of the particle, and photon is one of the very peculiar particles because this particle is the only particle which can move the speed of light. That's how light is defined, right? And for them, photon rest mass will be always zero. If I take like photon, it will be always zero. Also, just to complete the story in case of the interaction. So when I consider, first we consider gravitational force, which is one of the fundamental force. And till now, again, there is some interacting particle. Two massive objects, they interacting with each other. There should be one particle, it's called graviton. But there was many research going on related to this one. And it's also not belongs to Chandra model yet, but it is not discovered yet. So graviton is also expected as a particle is exchanging. So it could be boson, but it's not known yet because it's not discovered yet. And then there is a strong then electromagnetic force is the photon. Then there is one force, fundamental force called strong interaction. Or strong interaction basically the interaction quarks and gluons. So quarks they can interact with each other, and then they interact by a gluon, which is an interacting particle, and that is a very basic difference between the electromagnetic force and strong interaction. In case of electromagnetic force, two photons cannot interact. Though it is neutral, they cannot interact. But in case of strong interaction, when quarks they interact, they exchange gluon. So quarks are fermions, gluons are the bosons, and gluons are very fundamental. Gluons is a different character. Gluon can interact between themselves and they can exchange gluon. So because they are different dynamics. Because gluons are the very fundamental.
I think at some point of time, like we will be discussing about Higgs, right? I mean, so we'll discuss about
exactly. I'm going to say
how this field is interacting with Higgs to get mass. The gluons interact.
I am thinking a special class only dedicated to standard model. When talking about this one, so like just to complete the story, I would say about the strong interaction, and then when talk about the weak interaction. So my strong interaction was my PhD, where I did my PhD because strong interaction when quarks and gluons are interacting, so they had underlying theory. It's called quantum chromodynamics. Como is color. Color is like they have different color structure. And then there is weak theory, now which I'm doing my postdoc on that. So in weak theory, when there is any kind of decay, so this is one of the very popular and long time mystery when when they observe the decay of beta particle, and they see a kind of tail instead of just a simple peak or any just when, like, if you remember the experiment by Merkel, so he put a kind of, so this is a late one heavy object they consider, and they put one kind of radioactive element here, and on top of that there was a photographic plate, and it was like accidental discovery. I think my whole postdoc now is accidental one, because if this accident doesn't happen, then I should not. So then he observed there are some kind of, and so he put also a magnetic field later, and because of this magnetic field, he see is, so one spot here which is just directly come and hit on the plate, and it was
There's no charge.
A neutral charge particle, gamma particle, and also he find alpha and beta. So alpha is nothing but helium, and beta is a electron. And when you observe this beta decay, then it was very natural that when one particle come up, it's a particle. So it's just simply see one kind of spot here. Instead of that, he observed a distribution of energy. So when he found a particle, so he did one kind of, so this is a very common kind of, I don't know, you can see it or not.
I can see.
So we call this like distribution. So this is a notation which means that how many particles are emitted in a different
energy bins.
So when you observe this one, you see something like this. It was a distribution. So one particle comes, it's supposed to get only one heat here, or one particle. Everything will be stored at one point. Instead of that, we observe some kind of distribution. And I think it took like more than 30 years to solve why this distribution happened. And when they try to solve this problem, and then they find out, okay, there is something called some particle called neutrino, which is a kind of ghost particle. That neutrino take this energy of this particle, and then the concept of weak decay, weak interaction come into picture. So weak interaction is one of the another fundamental force in nature, which are responsible for the decay. And when weak interaction, there are three interacting particle, intermediating like photon or gluon. And one is W plus, which is one of the particle which is discovered, I think, in Shah in Geneva. W plus, W minus, and Z0. So there are three particles which are basically responsible for the weak interaction. Now, but standard model is not stop here. Though we've complete 4 fundamental force, there's one more particle, as you said, is Higgs, which I think one of the main reason why this LHC, Large Hadron Collider, was constructed, because the theory was suggested when they try to understand how the fundamental particle is getting mass. And the theory was suggested there should be one particle which creating an environment or field. It's called Higgs field. Field, as I mentioned, field is some infinite space, and it's assumed that there should be a space created by Higgs particle, and when any particle come closer to that, or is in that scenario, it getting mass. So Higgs was one of the fundamental particles which is discovered. If I'm not wrong, it's I think 1000. I forgot exactly which year. But it is on the era of 2000 something. But because of that, they got Nobel Prize. So this is a picture of standard model. So our main goal of this whole thing, it should be, so now here we're talking about this one. This is part of nuclear physics. So this is the part where we focus or try to understand when we talk about the nuclear physics. But apart from that, the whole particle zoo, like all these particles, how the dynamics, how they behave, how they interact, and how they can talk with each other. So this kind of thing we try to understand in the concept of particle physics.
Okay.
Yeah, so this
Um,
please.
yeah,
Yeah.
so we during the start of our conversation, right, we discussed about field and force. I think since we're talking so many things about field and right, from the way I understood, it's like each of this fundamental particle in the standard model, electron, mu1, tau1, everything, even the bosons, has a field, and excitation in the field gives rise to particle. This is my understanding. Excitation in the field gives rise to particle. Excitation in the electromagnetic field will give rise to photon.
Yeah.
So that's my
The second
understanding.
part is right, and the last part you said like excitation of the field that creating particle. So, but how the field is created, that is different story. So it may or may not be created by the like photon or the interacting particle, because at some point when you go some more mathematical details how the field theory is evolved. I mean, there's a computational subject, it's called quantum field theory. And this field, in that field theory, there are many different theoretical approach, as it means theory. So there are theoretical approach where they try to define how the field is constructed first of all, and if when they will feel how the particle interact with the field. Like when we talk about the Higgs, so like Higgs particle they create the field, and when other particles interact, I mean they are in the vicinity of this field, they get the mass. And the particle when we talk about the creating particle like proton and neutrons here. So when you're creating kind of particle, like you have only proton here and antiparticle or antiproton. So creating a particle is, as you mentioned, it is from the excitation of the state or the field. When there is an excitation, and the effect or the outcome of this excitation is a field particle. But how the
Correct.
create, that is a different story. That is not that particular quarks and gluons, but because it's the complete dynamics of all these fundamental particles when they interact.
Right. But
So
for the moment, I will assume like the field exists.
yeah,
Something for the
yeah.
just for the assume like the field exists, and then excitation in the field gives the particle. But what I'm difficult to understand is like is the following statement correct? Uh, we say that two charge part like electron interacting with another electron. So
Okay.
there should be like a medium. There should be like a force. So that force is called electromagnetic force. When two electron comes together, the interaction between these two electrons, these two particles, are the electromagnetic force, and that is mediated by the photons. So what I don't understand is like, um, uh, so the photons get the photon arise because of this interaction. Like what I'm reading is like for this these bosons are the force carriers.
Yes.
Bosons are the force carriers. Now these forces exist because these four particles interact with each other. So to me, it's like a chicken and egg. So if the particle interact, and that's why these photons are getting created. The particle interacts, so the photons are getting created. So is it correct to say that the particle interact with electromagnetic force? So is it correct to say like that?
It is not really generalized. It is correct in one sense. At some point, like if you see the final picture, that is true because when one positive charge particle, negative one, like as you said, one electron positron they interact or any charge particle interact. If you see the final outcome is okay. Two electrons they are interacting each other. They create their own field, and when they because of the field, the excitation of this photon is created, and this one photon is created here because of the excitation of the field here, which is created by the electron, and this photon which is created here, then it will be absorbed or annihilated when the other positron, which is create their own field, and that is annihilated there. So it is so and so this is kind of if it's the final picture is true because two electrons there, they are the exchanging between them because they are the carrier, and they for the Bose-Einstein statistics they had all criteria to fulfill the interaction. So photon is intermediate particle, But if you try to look into more closer one, so you have one electron here which is excited, and it's create its own field, and the field is excited, so it produces a photon. Now,
Hold on. So you said like the electron field is excited, produces a photon, right? So this what I don't understand. Like if there is no more electron, let's imagine there is only one electron. In the
yeah,
entire universe, there is only one electron. So that electron is coming because of excitation of the electron field. That's coming because of electron field. Now there will be no photons created, even though there is electron field, even though there is like this electron field, but there will be no photons getting created because there is no interaction.
okay, so just to extend your question, if I once again come back to this picture, like two proton charge, proton charge particle, a positive charge particle, they interact. They have very high energy. They interact.
Yes.
That is their field. Now here, see when the antiproton is created. So if there is, suppose there is no proton, then the symmetry will be broken.
Yeah. Yeah.
So
Okay.
it's
Okay. I see. So are you saying that there will be no scenario in which a single electron will be present in the entire the universe?
yeah, it could happen, but that is not. That means there is something wrong in the symmetry. I mean, if there is like the Higgs, they have their own symmetry. If you see some kind of very popular lectures, Higgs had this field or potential. It's called something looks like Mexican head potential.
Yeah. Yeah. Yeah.
But any like if I just think on that a Mexican hat on, if you take a ball and it's rotating here, so when it's rotating, and so it's excited the field. So and then and but if you see the field here, that if I just take a axis, so you have a symmetry between them. So when there is some symmetry, there is some conservation. But if there is nothing, there is not some conservation thing. If some conservation is violating because of some asymmetry, then this thing can happen, but it will be not physical one. It could be, you can think unphysical. It's possible. Like, okay, one electron is accelerated. So it could happen. This electron is accelerated, it produces one photon, it will be again absorbed. This could be
Okay.
happen.
Okay.
When
Okay.
instead of the Feynman diagram, then we will show a lot of diagrams where how this like is called self interaction. So like one electron is generated one photon and again it's absorbed by itself.
Okay. Okay.
Otherwise, the
Okay.
symmetry will be broken. I mean, this like here, photon is not come into picture. The basic fundamental symmetry will be broken because there should be a symmetry between matter and antimatter.
Gotcha.
Because matter, if you don't have this one, the matter and antimatter symmetry is broken, which is very fundamental one, because that's how the universe is constructed. So symmetry should be there. So okay, this thing is come when I talk about this Neutard theorem. So this lady Neutard, I think she is lady, if I'm not wrong. So she had a very beautiful theory in quantum field theory, a theorem in quantum field theory, that if in your system there is a conservation, that will come from symmetry. Or other way around, if in your system there is some symmetry that come to, that means there should be some conserved quantity. So
Okay. So if there is a conservation, there should be a symmetry. If there is a symmetry, there should be conservation.
should be conservation. The question I asked you in the beginning, that how the discussion started, like what are the conserved quantity or conserved thing we can think, like energy and momentum. So it is very common when say that energy and momentum should be conserved. The question is why. The answer is coming from there. If you go into more deeper in quantum field theory, in non-relativistic case, that this conservation coming from the symmetry.
Symmetry. Okay.
Like here, your momentum should be conserved because of this symmetry. Like if this proton and antiproton does not create, that means suppose two protons, they are
Colliding.
is produce two particles. Just forget, instead of one proton, just creating this one. So this antiproton, it will take some momentum. This momentum should be balanced by something. Otherwise, momentum should not be conserved. So momentum conservation, which actually belongs to that there should be a symmetry between matter and antimatter. Because you want momentum conservation. because that's if you define that it's a fundamental quantity, not a fundamental quantity, it should be conserved. So then your matter and antimatter should be there should be symmetry.
Gotcha.
It's
Gotcha.
a very
Okay.
basic thing which we use several times. Whenever we say there is some symmetry, that means there should be some conserved quantity.
Gotcha. Gotcha.
If
Okay.
there is no symmetry, something asymmetric, then it's called symmetry broken. I think the Higgs field itself, when I talk about the Higgs field, there is called symmetry broken. It's called spontaneous symmetry broken. So when you see this Higgs field, when this particle is moving in the Mexican hat, there is symmetry broken when the particle is moving there. And
Gotcha.
that asymmetry, basically creating this field, and which corresponding to that is produced in this particle, and because of that, all other particle getting mass.
Gotcha. Gotcha.
So
I'm sorry, like I need to go for the next meeting.
yeah.
This purpose meeting.
Okay, so I hope something is answered, and in the next class,
Yeah, definitely. Like I think a lot of my doubts got cleared. A lot of my doubts got cleared.
we'll try to focus on
So,
the notes.
so I will read more on the Griffith, and then I'll try to do the homework. Try to do the homework problem. Then probably we can discuss on the relativistic kinetics more detail next time.
Because this issue understanding is very important and very basic, but it's needed to understand really. Okay, thank you very much for joining.
Thank you so much. Thank you. Thank you, everyone. Bye.